Hi, I'm Fernando Pereira from UFMG, and today we shall talk about how to produce static program slices. To this end, we will see a notion of Hammock Graphs. Key to this construction, this notion has been introduced by Jean Ferrante in 1987 as a helping structure to track dependencies in code. These graphs are also known as single-entry, single-exit regions. So what's a Hammock graph? They are subgraphs of the CFG with the following property. They contain a node V and a node W, and here they are, so that every path reaching some node in the Hammock graph must pass through V. That's the single entry, the node V. And every path leaving the Hammock graph must go through W. That's the single exit node. Notice that in the Hammock region, we may have cycles, but not necessarily. And why is this important for program slices? Well, that's important because the nodes within a Hammock region are controlled by its entry point. So Hammock graphs help us to track control dependencies. And if we talk about the variable that controls some branch, like B0 here in the example, then we can define the influence region of B0 as the Hammock region that starts at the basic block where B0 is used in the branch. For instance, what's the Hammock region of B0 in this example? Think about the block that contains B0. Before we move on, let me clarify some nomenclature. When we talk about Hammock graphs, we are talking about relations between the basic blocks in a program. However, in the context of program slices, we will be talking a lot about the predicate that controls some branch. In this figure, P is the predicate that controls the branch at label ly. We shall mention ly instead of the basic block that contains it, as the same thing. So the Hammock region that's headed by this basic block that contains the branch that uses P, this basic block B right here, will be called the influence region of P. So this is the influence region of the predicate P. We call it like this because P determines which blocks will execute in that region. So for any basic block within that region, let's call it BC. We shall say that BC is controlled by the variable P, meaning that BC lays within the influence region of P. I've marked this region in orange here, the influence region of B0. We can define the Hammock region using the notion of post-dominance. Every path from a branch to the post-dominator of that branch forms the Hammock region. You can check this fact in the example. Notice that L8 is the post-dominator of the block that contains the label L1. Notice that if we use simple graph traversal to find influence regions, then we will have a costly algorithm. Imagine that we have to start a depth first search for every branch in the program. But there is an alternative to this approach, which is much faster. We will be relying on the dominator or dominance tree, as it's usually called, to build this alternative. So we will be designing a fast algorithm to identify control dependencies. Remember, node V dominates node U if and only if every path from the start of the CFG to U goes through V. And V is the immediate dominator of U if and only if any other node that dominates U will also dominate V. This is the dominance tree For our regional example, there is an edge from A to B in the tree if block A is the immediate dominator of B. And what does the dominance tree has to do with Hammock regions? The fact is that all the nodes that belong into a Hammock region of a predicate P lay under the node that contains P in the dominance tree. I know this sounds a bit confusing, but we shall see an example to clarify things. Let's start with a simple example. Label L19 is in the Hammock region controlled by the branch at label L18. Would you like to think on why this is true? Stop the video and think about it. By the way, every node dominated by L18 except its post-dominator belongs into the Hammock region controlled by the branch at L18. In this figure, we can see the dominance tree and the CFG of the program. The basic block marked in red controls the basic block marked in blue here. This fact follows from the definition of control dominance. The red block dominates the blue one, but the blue block does not post-dominate the red block. Do you remember control dependence? In practice, once the program flow arrives at the red node, it might visit the blue node or not, and that depends on the branch at the end of the red block. That's why, intuitively, we see that the red block dominates the blue one. Applying the definition of control dependence, we see that branch at L14 controls the block with labels L15 and L16 because L14 dominates L15 and L16, and it's not post-dominated by them. But L14 does not control L17 because L17 post-dominates L14. And that's the influence region of B0, which the predicate used in the branch at L7. L7 dominates every label from L8 to L22, and none of these labels post-dominates L7. If we look into the CFG, we can see that L7 controls the execution of all the blue blocks, but not the block from L23 to L24. In other words, depending on L7, depending on the branch on L7 right here, we might execute the blue blocks or not. However, regardless of L7, we will always execute L23 and L24 because L23 and L24 post-dominate this basic block here. So that was the definition of a Hammock graph, and with this definition we also saw notions like Hammock region, influence region, predicates, and so on. In the next class we shall see a functional algorithm to find control dependencies by traversing the dominance tree of programs. Till then, you feel free to write me with questions or comments.